Hi, and welcome to this next lecture on data structures and algorithms. We will continue our discussion on shortest path algorithms. In fact, we will continue our discussion for shortest path with a fixed source. However, today we will discuss an algorithm that can deal with negative weighted edges. Recall that we discussed the Dijkstra's algorithm, which operates under the constraint that no edge weights are negative. So, the Bellman algorithm, it computes shortest paths from a single source, fixed source, to all other vertices in a weighted directed graph. However, Dijkstra's algorithm does not work for negative weighted edges. It's a greedy algorithm that makes use of the optimal substructure property. Bellman solves the problem of negative weighted edges, but is slower than Dijkstra's algorithm. That's the price being paid. And the running time is order of number of vertices is to the number of edges. So what is the idea? So let us understand the algorithm with a simple example. So we will try and illustrate the working of the Bellman-Ford algorithm through an example. So let us say we have a graph with a source S. We will consider a purely directed graph. Let us give names to these vertices V1, V2, V3, V4, V5 and V6. We will also give names to the edges and their weights W1, W2, W3, W4, W5, W6. It also helps to have an additional edge here to make the graph a directed acyclic graph. So let us say this is W7. So the Bellman-Ford algorithm iterates through all the edges of the graph, and for every edge it determines the weight on the two nodes that it's part of. So of course if you have the edges to be undirected, it's possible that the shortest path crosses that particular edge in either way, in either direction. However, the edge is directed, you expect the shortest path from one node to another node, if at all, to occur only along the direction that is permitted by the edge. So the idea behind the Bellman-Ford algorithm is, well, initially all vertices are infinitely far away from the source. The source is of course at distance 0 from itself. Now you iterate over all edges. For each edge E, you are going to check if, so let us say E is going from U to V, you will check if the distance, the shortest path distance to V, existing distance, is greater than or equal to the distance to U plus the weight on the edge UV. If this is the case, then you update dV to this new found shortest path, which says I am going to look at the shortest path to U and then append the edge UV to the shortest path to U. So this is the basic idea, and you are going to do this for every edge. How many times will you have to do? Well, when you start the iterations, initially you determine that for V1 and V4, or that is the edges W1 and W4, you are able to update the weights for V1 and V4 to say W1 and W4 respectively. However, for all the other vertices other than source, of course, in the first iteration over all the edges there is nothing to update. However, in a subsequent iteration you will also update the shortest path for V2, say, which is W1 plus W2, and that for V5, which is W4 plus W5. So you will have to iterate over all the edges number of times that equals the maximum number of hops to a node from S. So number of times to iterate over all the edges. What I mean by this is this iteration. This is the width of graph, which is max number of hops from source node S to any vertex, say this, let us say V. Well, by the way, we do not need the V6, so I am just going to use V3. So this is going to be V3. So the complexity is basically number of edges into this maximum number of hops. But I will convince you that this maximum number of hops in the worst case actually happens to be number of vertices minus 1. I will construct an example to show this. So let us consider a simple linear graph. S goes to V1, goes to V2, goes to V3. So my first scan over the edges, I will be able to update V1. The second scan I will be able to update V2. The third will be V3. So there are 4 vertices and I need 3 scans over all the edges till I am able to reach V3 and update its shortest path. Because I can update the shortest path for V3 when the shortest path for its immediate neighbors are updated. Let us look at the actual algorithm. As pointed out, the first thing you do is iterate over all the vertices, set the depth of every vertex, the shortest path to depth to infinity. The predecessor for all the nodes is not set, but the predecessor for the source is null and the depth for the source is 0. And then, as suggested, we are going to iterate over all the edges, this inner loop, iterate over all the edges, and we are going to do that for a number of times that equals number of vertices minus 1. So recall that this is, in the worst case, the so called width of the graph. And then it is a check that we already anticipated. If du plus w, w is the weight of edge E, if this happens to be less than the existing shortest path distance to V, then you update the shortest path distance at V. You also update the predecessor of V to point to U. So this is already motivated and explained. What is the part here at the end? Well, so far we have assumed that our graph is a directed acyclic graph. What if the graph has cycles and is therefore not a directed acyclic graph? Abbreviated as DAG. Even in the case that the graph has no directed edges, it might just have cycles. And here is a test. If the shortest path can be further reduced even after V minus 1 iterations, then it appears that there is a cycle, that is there is a path from S to a node, any particular node that involves a cycle. Let us illustrate this with an example. So we have S V1, let us say this is weight 5, this is say 4 to V2, V3 minus 3. We already pointed out that negative weighted edges are possible, and say minus 2, minus 1. Now as you update the weights originating with S, 0, V1 is 5, V2 is 9, V3 is 6, and then you have 4, and then you have minus 1, 3. However, the next iteration when you update V2, you will get 7, and then you will be able to update V3 to 4, and that at this node V4. You are able to update the weight for V4 further and get it to 2, and then at V1 get it to 1. You could do this again, go over this. 1 plus 4 is 5, 5 minus 3 is 2, 2 minus 2 is 0, 0 minus 1 is minus 1, and so on. So just by going around this loop you can actually get very negative weighted paths from S to all of these nodes. So what is a characteristic here? Well, it turns out that this cycle itself has negative weight. What is the weight of all paths on the cycle? Minus 1 plus 4 plus minus 3 plus minus 2, the whole weight is basically minus 2. So the more you go around in this loop, the more you will be able to reduce the shortest path, and this you can do ad infinitum. So this is what we are checking. If after so many iterations, if you are still able to reduce the shortest path distance to any particular node, then you basically can't find the shortest path. So just return a false. So that is what we see here, returns false for negative weight cycle. Let us see this in action. We start with infinite weighted shortest path to all the nodes. In the first iteration over all the edges, we find that only the immediate neighbors of the source can be updated, and we have done that. Then again we look at all the edges, we are only able to update now the immediate neighbors of these nodes that were updated. So it turns out that B is also neighbor to A, and you are able to get shortest path to B through A. This is the latest. We continue our bookkeeping, find that the shortest path to C and D has been updated, C and E has been updated, and then to G, and it turns out that you can actually find another shortest path to G through C, and in fact this also lets you update shortest path to E through G. So let us analyze the Bellman shortest path algorithm. We look at two characteristics, one is its correctness and the other will be its complexity. So we prove the correctness of this algorithm by claiming the following loop invariant. And we state that for every vertex V within k hops from the source node S, the value dV is indeed the shortest path from S after k outer iterations. So we are claiming that at the kth iteration of this outer loop, the value that gets updated in dv at the end of this kth iteration, dv contain the correct value, the shortest path. And it's easy to show that at initialization this is correct, because the only node that is within 0 hops from the source itself, and indeed the depth of the shortest path of source is set to 0. The next iteration we can easily see that we only deal with the immediate neighbors of the source and they get updated correctly. In fact, the maintenance can be easily proved, because we know that to get to a vertex which is k plus 1 hops from the source S, you need to go through a vertex which is within k hops from the source S. So maintenance can be proved with the key observation that a vertex at k plus 1 hops from S is reached through vertex at k hops from S. And this can therefore extend even at termination. What about time complexity? Well, the runtime complexity is again straightforward. As we had anticipated, we are going to iterate over all the edges for a fixed outer iteration, and the number of outer iterations is basically the number of vertices out of the number of vertices. We have actually split the cost here for each of the if blocks and the for loops and so on, but it's essentially number of edges into number of vertices. The final check is only order of number of edges, which is basically to check for negative edge cycles. So overall complexity is order of VE, is the dominating term. Thank you.